When you need to measure a variable amount of liquids to high precision, the Buret is a handy option. All Burets look pretty much the same. They're long and skinny with graduations and a stopcock on the bottom. They differ from a graduated cylinder in that the liquid is added to the top but dispensed from the bottom. Lloyd is going to help us demonstrate the proper use of a Buret. The first thing we need to do is condition the Buret. Start by closing the stopcock and adding a few milliliters to the Buret. Now take those few milliliters and rinse them around back and forth to wet all the surfaces on the inside of the Buret. Be sure to keep a waste beaker handy to collect your rinsings. Also, be sure to run a little bit through the stopcock as well. Now you're ready to fill. You can use a funnel or not. And here's a pro tip. When filling your Buret, be sure to remove your analyte flask that contains your solution away from the bottom of the Buret. That way, if you spill any of the solution you're pouring into the Buret, it doesn't contaminate the analyte solution. You don't have to fill up the Buret all the way to zero. Get it up pretty close to the first trial. You'll have a better idea of your volume after the first trial. You'll waste time getting it exactly to zero. By this time in your educational career, you should be able to handle simple subtraction. Let's focus on reading the Buret. Unlike the graduated cylinder, with a Buret we read from the top down. Notice the graduations. On this device, the graduations are each worth 1/10. 0.1, 0.2, 0.3, 0.8, 0.9, 1.0. Like all glassware, we're going to read this at eye level. Like our graduated cylinder, we're going to zoom in with our mind's eye and further divide the space between two graduations into 10 parts. For this Buret, each graduation is 0.1. We divide each of those 0.1 graduations into 10 parts, making each of those 10 parts 0.01. This means that our Buret can be read to the hundredths place. Reading from the top down, we see our reading would be 4.69. Since the 9 is our estimated digit, it is called the doubtful digit, and our measurement is good to 3 significant figures and 2 decimal places. Let's do a simple acid-base titration, where we titrate a sample of hydrochloric acid with sodium hydroxide. The acid is our analyte, and the base is our titrant. In this case, the acid is hydrochloric acid, which Lloyd has carefully measured 10.00 milliliters of the acid into the flask using a 10 milliliter pipette. In order to determine the endpoint which tells us when to stop the titration, we'll need an indicator solution. In this case, we'll use a solution of phenolphthalein. Lloyd has already conditioned his Buret, so he can go ahead and fill the Buret with the titrant sodium hydroxide. Don't forget to add the indicator solution, or else you will titrate forever and not know where the endpoint is. The indicator solution changes color to tell us when all of the analyte, hydrochloric acid, has been neutralized. Initially, titrations are slow going. The first trial will be the slowest. After the first trial, you will have enough information to speed up subsequent trials. Be careful, the endpoint can sneak up on you very quickly. Don't go past it. Initially, you will add larger quantities of solution, and as you get closer to the endpoint, you will begin to add smaller quantities. Keep your wash bottle filled with deionized water handy. Periodically rinse down the inside of the flask to make sure all of the titrant has made it into the analyte solution. Notice that the solution is temporarily turning pink. This is because of the phenolphthalein, and the closer you get to the endpoint, the more persistent that pink will be. The goal is to get to the faintest persistent pink with 1 drop or less of titrant. You can add less than 1 drop of titrant by carefully opening the stopcock to let a small amount of liquid build up on the tip of the Buret. Then touch that tip to the side of the flask and rinse with water. Your titration is finished when the solution changes to a faint, persistent pink. Darker is not better. Let's take the final measurement and do some calculations. We started the titration with a volume reading on the Buret of 4.69 milliliters. When the titration is completed, the reading on the Buret is 14.71 milliliters. To find the volume of the titrant added, in this case sodium hydroxide, we subtract the two values, which gives 10.02 milliliters. Now we have enough information to calculate the molarity of the acid solution. Molarity is a unit of concentration and is defined as moles of solute per liter of solution. Since we are interested in the molarity of the acid solution, we need to know the number of moles of acid in a quantity of acid solution. Lloyd has already measured the volume of the acid with a 10 milliliter pipette, so we have that piece of the puzzle. We now need to convert to liters. There are 1,000 milliliters in 1 liter, so we can apply this conversion factor to get 0.01000 liters. The titration data will be used to calculate the number of moles of acid in the solution. To do that, we need the balanced chemical equation to give us the stoichiometric ratio. For the reaction between sodium hydroxide, the titrant, the hydrochloric acid, the analyte, the stoichiometric ratio is 1:1. For every mole of sodium hydroxide added to the flask, it reacts with a mole of hydrochloric acid. From the Buret reading, we added 10.02 milliliters of sodium hydroxide. Because of limited screen space, we will have to break this calculation up, but it could be completed in a single line. The next goal is to determine how many moles of sodium hydroxide Lloyd added to the flask. We can figure this out by multiplying the volume of the sodium hydroxide in liters by the molarity of the sodium hydroxide. Where do you find the molarity of the sodium hydroxide? It is on the container where you obtain the solution. Make sure that you record this in your lab notebook. In this case, the molarity of the sodium hydroxide is 0.5014. But for your experiment, it may be something different. Let's include this molarity in our calculation. Liters are on the bottom, so that we can cancel out the liters of sodium hydroxide added. Now we're ready for the mole-to-mole ratio. This can be found in the balanced chemical equation and allows us to determine how many moles of acid were neutralized by the sodium hydroxide. Remember, the indicator solution showed us when to stop. It changed color when all of the acid was reacted. Now we have the missing piece of our puzzle, the number of moles of acid in the flask. Dividing the number of moles of acid by the volume of the solution yields the molarity of the solution with units of moles per liter. Thanks, Lloyd. Oh, and one more thing. Be careful with those Burets. They're very expensive.